A very good morning to all of you students. So we are learning discrete mathematics subject, and in this today's topic of discussion will be trees from unit 5. Graph we have covered, and today we'll be covering trees, rooted trees, spanning trees, minimum spanning trees. So what is the definition of a tree? We'll try to identify the keywords related to that. Okay, tree is a graph. Tree has nodes. A tree has one node which is called as the root node. So that root node will be having an in degree 0. Every node other than the root node has in degree 1. For every node there is a directed path from the root to a leaf or an internal node. So these are the keywords related to the definition of tree. What are the keywords? A tree is a graph. A tree has nodes. A tree has a special node called the root. That root node will have an in degree of 0. Other than the root node, all the other nodes will have the in degree of 1. Okay. So this is the diagram of tree. Okay. Here A is a node which is a special node. It is a root node. Why it is a root node? You can see the in degree is 0. If you take B, okay, the in degree is 1. C, the in degree is 1. Okay. So these other nodes will be called as the internal nodes. These will be called as an internal node. Here you can see that if C is a node, this is C node. The sons of C will be F, G, H. You have, let's say, I. Okay. So E, F, G, H, I, or take any node. If you want to find the ancestors, you can say A is an ancestor of, say, H or K or J or L or I, like that. Now this graph is not a tree because you don't find any root node and you find the in degree to be 2. Let us take this tree and verify whether it is a tree or not. So as per the definition of tree, does it have nodes? Yes, it has nodes. How many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes are there. Okay. Now this is the root node because the in degree is 0. Rest of the nodes, the in degree is coming to be 1. So it is following the definition of a tree. You can see here we are also labeling the levels here. At the root it will be level 0. At the next it will be level 1. At the next it will be level 2. At the next it will be level 3. Okay. So here maximum level is 3. This maximum level 3 is called as the height. Okay. What is this height? Height is the length of the longest path from root to leaf. It is the length of the longest path from root to leaf. Okay. So let us go for the next keyword in the tree topic, search tree. So for that, let us understand what is a ternary tree. What is the definition of a ternary tree? Each node will have either 3 or 2 or 1 or 0 sons. Say for example, this node is there. How many sons are there? 3. This node is there. How many sons are there? 3. This node is there. How many sons are there? 2. This node is there. How many sons are there? 2. So, as per the definition of a ternary tree, every node will have 3 or 2 or 1 or 0 sons. Coming to binary tree, the definition of binary tree, what it says, every node will have 2 or 1 or 0 sons. For example, this root or this node will, what is the, how many number of sons are there? 2. This node, how many sons? 2. This node, how many sons? 1. So ternary sons will have 3 or 2 or 1 or 0. Binary tree will have 2 or 1 or 0. N-ary will have n sons. So if it is a complete n-ary tree, each node will have I sons, and the value of I will be in the range 0 is less than equal to I, less than equal to n. So if it is a complete n-ary tree, each node will have 0 or n sons. If it is a complete binary tree, each node will have 0 or 2 sons. For example, this node 2 sons, 2 sons, this node 2 sons, this node 2 sons, this node 2 sons. So these two are complete binary trees. Let us check this. This node 2 sons, this node 2 sons, this node only 1 son. So this tree, the rightmost tree, does not fall under the definition of complete binary tree, because what is a complete binary tree? It will either have 0 sons or it will have 2 sons. What is the use of binary trees? They are used for search. There is a formula for the height of a binary tree. So it falls under in this range. H plus 1 less than equal to n, which is less than equal to 2 to the power of h plus 1 minus 1. So here h is the height, n is the number of nodes. So let us take this as per the formula. Let us take this, let us say this tree. Okay. So if you count the number of nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So total number of nodes for this tree is 15. Let us go for the height. Level 0, level 1, level 2, level 3. So the height of this tree, will be 3. Now what is the formula? The formula for the height is like this: h plus 1 less than equal to n, which is less than equal to 2 to the power of h plus 1 minus 1. So here we know height is this much, nodes are this much. 2 to the power of h plus 1 will be equal to the power of 4 plus 1, sorry, 3 plus 1, 4. 2 to the power of 4, which is 16. So 2 to the power of h plus 1 minus 1 will be 15. So this is falling in that range. Similarly, you can take this tree also. If you see the number of nodes here, 1, 2, 3, 4, 5, 6, 7, 8. So the total number of nodes for this tree on the right side is 8. The height again is level 0, level 1, level 2, level 3. So the height is 3. So h plus 1 is less than equal to n, which is less than equal to 2 to the power of h plus 1 minus 1. So what will be h plus 1? That will be 4. What will be n? N will be 8. 2 to the power of h plus 1 will be 16 minus 1, 15. So it is falling in the same range. It is a binary tree. Will be used for searching. What you have to do is you will be storing your records in the form of a tree. The search will take log n time, and search will be done through a unique key. Say for example, this is your tree. Okay, so you have stored records in this tree. Now say, let us say you want to find a record number 9. What you have to do is you have to go to root and you know that on the left side all the nodes their values are less than the root. On the right side all the nodes the values are greater than the root. So as 9 is greater than this root, we are going on the right side. So the first node is 10. So as 9 is less than 10, we are going on the left. So this way you will be traversing and you will be searching your node. Or the alternative way is you can store the records at the leaves, and at the internal nodes you will be storing the discriminating values. Okay, for example, here 12 is the discriminating value, and do the search. So we have been saying that binary trees will be used for search, okay, and search will be done using traversal techniques. And which are the traversal techniques? We know that there is a pre-order traversal, there is a in-order traversal, and there is a post-order traversal. So how will be traversing when it is pre-order? Go to the root, then the tree 1, then the tree 2. In order, here tree 1, tree 2 will be as left tree and the right tree, okay. So in order, so you will be going to the tree 1, then the root, then the tree 2. Post order you will be going for tree 1, then the tree 2, then the root. So if it is in order, you know that start with left, go to the root, then go to the right. If it is pre-order, start with root, go to the left, then the right. If it is post order, go to the left, go to the right, then the root. You can see here the traversal for this tree, okay. This is my tree with the nodes A, B, C, D, E, F, G, H, and this is the pre-order traversal for this. What is the pre-order traversal? Start with the root, then go to the left, so that is B. Start with the root is A, then go to the left is B, D, E, G, then go to the right, that is C, F, H. So if it is in order, you know that start with the left, then the root, then the right, okay. So when I'm starting with the left, go to the extreme left, that is D, then B, then G, then E, then the root A, then C, then H and F. If it is post order, start with the left, then the right, then the root. So root will come at the end. You can see here the root is coming at the end. So we're starting from D, then G, then E, then B, then H, F, C, then A. So this is my traversal. Here you can see in this tree also the pre-order traversal will be A, B, C, D. In order traversal will be B, A, D, C. So let us see whether this is a tree. As per the definition of tree, what it should have? It should have nodes. It has nodes. It should have a root node, and the in-degree of the root node is 0. It has it, okay. Then the other leaves will be there, intermediate nodes will be there. In this tree, you know the level starts with level 0 at the root, level 1, then level 2, then level 3. So the height is 3. Height is 3. If you see a node called as 7, and we know that 7 is a root node, we can say 7 is the ancestor of 13. 13 is the descendant of 7. If you take this 3, we know that 3 is the parent of 1 and 5. And 1 and 5 are the children of 3. You can see 7 has two subtrees, one with 3 and its descendants, the other with 11 and its descendants. The end vertices are 2, 4, 6, 8, 10, 12, 14. These are also called as the external nodes, and they don't have any children. So I want to check whether my binary tree is a binary search tree or not. I want to check whether my binary tree is a binary search tree or not. But before that, let us look at the meaning of a binary search tree. Binary search tree is a binary tree, but for every node value of the node in the left subtree is less than or equal to the value on the node in the right subtree. So let us say this is my root, this is the binary search tree, this is binary search tree. So the left side value will be less than or equal to the right side value, and the right side value will be greater than or equal to. Binary search tree will be used for quick search and updates, inserts and removals, arrays and linked list. Okay, so if you are searching a linked list, the search time will be O of n. If you are inserting O of 1 at the head, O of n at the tail. If you are removing O of n. The complexity for binary search on sorted list is O of log n. So let us look at the definition of, we have seen the definition of binary search tree. Let us check whether these trees are binary search trees or not. Here, this is my root node with a value of 8. So whether it is a binary tree, what is the definition of a binary tree? Binary tree will be having 2 or 1 or 0 children. So 8 is having 1 child, 6 is having 1 child. So it is falling under binary tree. Is it a binary search tree? 8, the value of the root is 8. So the left side is less. So it is binary search tree. Now whether this is the second tree is a binary tree or not. What is the root node here? The root node is 10. Okay. So its in degree is 0. Okay. How many children it has? 2. How many children this 5 node has? 2. How many children this 4 node has? 1. How many this children this 7 node has? 11. So as per the definition of binary tree, what is the definition of binary tree? It will be having 2 or 1 or 0 children. So it is a binary tree. But is it a binary search tree? So to check, I need to go to the root. The value of the root is 10. On the left side, I need to check all the values are less than 10. And on the right side, the value is 16. But on the left node 5, it is also having a right node 7 whose value is 11. So this is not following the definition of binary search tree, because the left side value is not less than, it is greater than. Let us take the third tree here. The root node is 7. The value is 7 here. So on the left side all the values are less. On the right side the values are more. So this is a binary search tree. The rightmost tree with the root node 5. Is it a binary search tree? Left value is less than, right value is greater, but for this 8 node, the left value is bigger. So this also does not fall under binary search tree. Even this root node is 15. The left values are less and the right values are more. So this falls under binary search tree. Let us try to understand what is a minimum spanning tree. What is a Kruskal's algorithm? So MST, this is the short form for minimum spanning tree. Okay. So minimum spanning tree will have minimum weight. It will have connected vertices without cycles, and minimum edge weights will be there. So let us see if any definition is mentioned. Let me check if somewhere I have written the, yeah, I have written the definition here. A spanning tree is a graph, but it is a tree. All its vertices are connected by some edge. Okay. In a spanning tree, the number of edges will be equal to n minus 1, where n is equal to number of vertices. So what we have understood by spanning tree, it's a graph, but it's a tree, but its vertices are connected by some edge. All the vertices are connected by some edge, and the number of edges will be equal to n minus 1, but it is vertices minus 1. And what is a minimum spanning tree? It has minimum weight. Minimum spanning tree has minimum weight. So How to derive a minimum spanning tree from a graph? Let us check. Okay. This is my graph. Is it a graph? Yes. Is it a graph? Is it a tree? No, it is not a tree as of now. So this graph has how many vertices? A, B, C, D. So four vertices there. How many edges this graph has? 1, 2, 3, 4, 5, 6, 7, 8, including the loops. There is a loop at A, there is a loop at D. So the number of edges are 8, okay? Because A and D are loops. So this is my graph. Now from this graph, I have to derive a minimum spanning tree. From this graph, I have to derive a minimum spanning tree. What is the definition of minimum spanning tree? Okay. First, we need to remember what is a spanning tree. Spanning tree means what? All the vertices are connected by the edge. All the vertices are connected by the edge. Okay. And there will be minimum weightage on the edges. So, for deriving a minimum spanning tree from a graph, there are two techniques mentioned. One is Kruskal's algorithm, K-R-U-S-K-A-L, Kruskal's algorithm. So we'll directly implement the Kruskal's algorithm and then we understand what is a Kruskal's algorithm. Kruskal's algorithm is used to derive a minimum spanning tree from a graph. So what is the first step we have done here? We have removed the loops. So where are the loops? A has a loop in this graph. D has a loop in this graph. So these two loops are removed. You can see here this new graph, it doesn't have the loops. What is the next step being mentioned? The next step being mentioned is remove parallel edges. Which parallel edge you will be removing with higher weight? So are there any parallel edges in this graph? Yes, A to C. A to C, one weight is 2. A to C, one weight is 12. So which parallel edge we are going to remove? We are going to remove the parallel edge with weight 12. So here I have removed, you can see here the parallel edge A to C with weight 12 is removed. Now after that, what we have to do? We have to create an edge table. Okay. How we are going to create the edge table? In ascending order. So the edge table will have two columns. One will be listing out all the edges, the other one will be listing out the weights. Which are the edges with minimum weight? Let us say BC is the edge with weight 1, lowest. Then AB is the edge with weight 2. Then AC is the edge with weight 2. Then CD is the edge with weight 3. BD is the edge with weight 5. So this is in ascending order. Lowest weight is 1, highest weight is 5. Now, how many vertices are there in my graph? 4. So in a spanning tree, how many uh, edges will be there? 4 minus 1, 3. So 3 edges will be there. Our minimum spanning tree will have 3 edges. So from this edge table, we have to take 3 edges with a minimum weight. We can take BC, then we can take AB. But if we take AC, what will happen is BC and AB. Then if you take AC, this forms a cycle, and this does not. It is not a tree. It is not a tree. So what we'll be doing is we'll be rejecting AC. What we'll be doing is we'll be rejecting AC. So instead of AC, we'll be taking CD. Instead of AC, we'll be taking CD. So now this I have taken AB, BC, CD, and I can calculate the total weight. How I can? So I have taken AB. So I have taken BC 1. I have taken AB plus 2, 3. Then I have taken CD. So 3 plus 3, 6. So that will be 6. The total weight will be 6. This is my minimum spanning tree. Same here, let us say I want to find the minimum spanning tree. What I have to do? Remove loops. Are there any loops? No. Remove parallel edges. Are there any parallel edges? No. What is the next step? Create an edge table. Okay, which are my edges with the minimum weight edges? AB, then BD, then DC, then BC, then AC, starting with 1, ending with 3. How many vertices are there? 4. How many edges will be there? 3. So I have to identify three such edges. So what are the three edges? I can go for AB, then BD, then DC. That's it. All the one with three we have taken. AB, BD, DC. Similarly, this is a graph. From this graph, can I extract a minimum spanning tree? Yes. What are the steps? First, remove loops. Are there any loops? No. Then remove parallel edges. Are there any parallel edges? No. So then create an edge table with minimum weights. So first take all the edges with weight 1. We have AD, then we have BC, then we have CD, DC. Then take with 2, and any edge with 2, yes, EF. Then take with 3, any edge AB is 3, then BD is 3. Then take with 4, CF is 4. Take with 5, you have CES5. Take with 6, DES6. So how many vertices are there? 1, 2, 3, 4, 5. 6 vertices are there. How many edges will be there? 5. So I have to take 5 edges. So we'll take AD, BC, DC, AD, BC, DC. We have taken AD, BC, DC. Then we can go for EF also, but we cannot go for BD because that will create a graph or a cycle. So I can go for CF. Yeah. So this is it. You have AD, BC, DC, CF, and then EF. So total weight will be 9. You can try for this graph also. Just you know that in this graph also there are no loops, there are no parallel edges. Just create the edge table starting with 1 till 9. And how many vertices are there? You have 1, 2, 3, 4, 5, 6, 7 vertices. So how many edges will be there? You will be having 6 edges. So pick out the edges and create a minimum spanning tree using Kruskal's algorithm. The time complexity is OE log E. Now the other technique to derive a minimum spanning tree is Prim's algorithm. How Prim's algorithm is different from Kruskal's algorithm? Here we have to take a vertex and we have to make a list of edge with lowest total weight. Here we have to find total weight. So let us say this is my graph and I want to find the minimum spanning tree for this graph. What I will be doing? I will be first checking how many number of vertices are there. 1, 2, 3, 4, 5, 6. So total 6 vertices are there. So how many edges will be there in the minimum spanning tree? 5. N minus 1, 6 minus 1, 5. Now what is the next thing I have to do? I have to make a list of each of the vertex with total weight. I'll go with A. A node is there, A vertex is there. What is the total weight of A? 13. What is the total list weight of B? 16. Total weight of C? 16. Total weight of D? 27. Total weight of E? 13. Total weight of F? 15. So I know that now I have to take minimum weight edges. So which is the minimum weight edge? So 13, then 13, then 15, then 16, then 16. So like that. So we'll be taking the edges AB, AD, CD, CE, EF. So this becomes my new graph, and the total weight for this minimum spanning tree, and the total weight for this will be 17. You can check here also one more example, and you can try this using the Prim's algorithm. So this was our learning for trees. Thank you.